Okay, we all set? Any questions about anything before we start? Small, intimate group today. A new device on Alex's arm.
No,
Same old device. Yeah, okay. I don't know if you guys noticed, but your classmate who's not here today, Shane, who was the other guy with the cast on, was prominently featured on the front page of The Sun and on the front page of the Ithaca Journal website for his thing that he did for 4760, the thing where you get close to a wall and it vibrates on your hand, so if you're blind, you could, know when the wall is coming up. I forget what the name of it is, but what is it? Pulso? Pulso. But anyway. Okay. So, I'm sure a lot of you are watching this over spring break. I hope you're having a good time wherever you are. Anyway, remember where we were at last time? We finished the discussion of the generalities about the standard genetic algorithm, and I talked about the Schema Theorem. And what I want to do today is carry on with the discussion of why the Schema Theorem really doesn't explain how genetic algorithms work, and give you a bunch of examples from the literature to illustrate that. Okay, so at the very end of class last time, I said the following. I said that there's nothing wrong with the Schema Theorem. There's nothing wrong with it, but what the problem is, there's lots of sort of misconceptions, and these have been abating over the years. About how much it says, how much it explains how GAs work. And the reason that people sort of got hooked on this idea that the Schema Theorem explains how GAs work was that they believed everything that Holland said. Now, Holland is a very imaginative guy. And if you read his book, you'll see that some of the math is very imaginative, too, in the sense that it's wrong. But, he misuses Stirling's formula numerous times, all that kind of thing. But that's all right. He's a computer scientist, right? Oh, sorry.
It's all good.
Yeah, it's all good. Okay. So here's Holland's view, Holland's original view. And his view includes a lot of sort of language, kind of inflammatory names for things that are very illustrative and very seductive and all that sort of thing, and I'll try to go over that. So Holland's view was the following, that in biological evolution, you can visualize the development of sort of effective problem-solving creatures as essentially developing genomes that encode for a variety of useful proteins. So when I say development, I'm not using development in the technical biological sense. I'm using it in the following sense: development via selection, mutation, crossover, etc., of genomes that encode a variety of quote-unquote useful proteins. Because really, solving biological problems is about having the right protein to do whatever job you're trying to do. How do these things get built up? How do these genomes that encode for a variety of useful proteins get built up? Well, remember, hemoglobin has only 146 amino acids. It's a relatively small protein, right? So protein encoding pieces of a genome, even if they're not contiguous, tend to be rather small. So protein encoding sequences, pieces, whatever, of a genome are relatively short. Okay? So you can imagine that maybe just by happenstance, just by whatever, things falling together, one of these things ends up in a genome and it gets propagated because the bodies that have that genome in them get selected for reproduction because that protein is useful, it helps for survival and all that sort of thing, and it sort of gets locked in. Okay, so they get sort of locked in over time, and maybe one parent that has one useful protein in its genome meets another parent that has another useful protein somewhere else in its genome. They mate, they cross over, and voila, one of their offsprings has encodings for both useful proteins in its genome. And those encodings don't tend to get broken up because they're relatively short. The crossover doesn't, with high probability, the crossover doesn't happen in a sense that breaks them up. Okay, so recombination, crossover, tends not to quote-unquote break these short sequences. But instead to combine them. In the offspring of parents, say one parent has one parent has another, and lo and behold, you build up over time genomes that encode for a variety of useful proteins. Okay, so that's a very simplified view of how you can think of biology as solving problems via selection, mutation, crossover, etc. Okay, so Holland was hoping that this is what genetic algorithms are doing. That you have these bit strings, this population of bit strings, and relatively short sequences of bits that are locked in over time are ones that encode something useful about the problem solution. So in a sense, what he's talking about there is a schema. He visualized a schema with relatively short defining length. So Holland saw a schema of relatively short defining length. That's one property. And with relatively few fixed bits, he thought of these things as analogous to sets of genomes that have a useful protein encoded in some relatively short, relatively few defined nucleotide places. So these are analogous to sets of genomes, each of which encodes the same useful protein. And this lecture, by the way, is going to be mostly pretty non-mathematical. It's going to be more philosophical and try to give you an idea, of some of the big problems here associated with Drew.
Just a question.
Yep.
You mentioned that the crossover tends not to break those short sequences.
Yeah.
Do you think, are there any genetic algorithms that try to find places that aren't good to cross over and avoid crossing over those places?
Not that I know of, but probably somewhere somebody's done that. Actually, I forget the answer to that question. And maybe in Chapter 3, when we read Chapter 3, I forget what's in Chapter 3 exactly, because that's more about, look at all the wonderful things people have used GAs for, which they have, by the way. But no, I don't know the answer to that question. Okay, so anyway, Holland saw this as kind of an analogous thing, and he gave a name to schemas with relatively short defining length and relatively few bits. He called them building blocks. So a building block for Holland is such a schema. A schema with relatively short defining length and relatively few fixed bits. And he thought that what was happening in genetic algorithms was, just like in biological evolution, the genetic algorithm was comparing such schemas with each other and selecting them if they're short defining length, relatively few bits, fitness on the average was higher, recombining them like this. So you're building up bit strings that are members of high average fitness schemas. Okay, and he called that process implicit parallelism. So that's another one of those very freighted kind of phrases that he made up. So he saw GAs as sort of running schema competitions. Many at the same time, many competitions at the same time. And he called this process implicit parallelism. Okay, so that in some sense, what's going on there, without any kind of design, without any kind of, sort of computer scientist sitting down and writing up a parallel architecture, that GAs were automatically running this parallel kind of computation, and all the different computations that were running in parallel were these schema competitions, and building up bit strings that feature high average fitness. And I'm going to put that phrase, I'm going to underline it, and I'm going to put it in a box, because this turns out to be a big problem that we're going to talk about in a second. High average fitness schemas. And when I say they feature that are members of high average fitness schemas, okay. Now, what's the problem here? The problem turns out, well, one problem turns out to be, here's a difficulty with that box thing with a star around it. Holland's view of high average fitness schema was the following. So Holland thought of the average fitness of a schema, and our terminology, our notation for schema is H. Does everyone remember why H is the name for schema from last week?
It's a filter transfer function.
That was your guess last week, and it was equally wrong today. Hyperplane. Yeah, okay. So fitness of a schema H as follows. 1 over the number of strings in the schema times the sum over all y in the schema of f of y. Straight up arithmetic mean. I'm using the standard set theoretic notation. Absolute value around a set is the number of elements in a set. Now, the problem with that is that if you think about the size of schemas and the size of populations and all that kind of thing, the size n of a population in a GA is generally much smaller than the size of a schema H. Think about it. Populations in genetic algorithms are usually on the order of 100 or hundreds, right? But the size of a schema is kind of exponential in the length of the bit strings, right? So if you have bit strings of length L, and especially it's even worse when you have a schema that has relatively few fixed bits, okay? Because that's going to be, the size of that schema is going to be 2 to the number of stars in the schema's defining symbol. So, in fact, H is even bigger when H is a building block in Holland's sense. So there's fewer defined bits. Thus, when you look at a population at a given time in a genetic algorithm, you're only looking at a tiny fraction of the strings in the schema H, no matter what H is. And therefore, you should not expect those representatives of H necessarily to have anything to do with the overall arithmetic mean of the fitness of the strings in the schema. Okay, so thus any population contains only a small fraction of the members of a schema H. So there's no reason to think that the static average fitness of H, and that's the name that people give to this. This thing here is called the static average fitness of H. No reason to expect that the static average fitness of H is represented by these guys, these members. And that's where the math falls apart if you look at Holland's proofs of things. Okay. All right, so that's a very general comment. Now, what I want to do now is I want to give you some examples from the literature that illustrate different situations, you know, what's going on, and some of these are about schemas and some of them aren't. So the background thought that you're supposed to carry through this discussion is the following. Really, quote unquote, what's going on in a genetic algorithm has to do with a complicated interplay between all the different pieces. Especially, so really, what's going on in a GA depends on the complicated interplay between the encoding. Remember, what is the encoding? The encoding is some mapping G from 0, 1 to the L. If we're talking about the standard genetic algorithm, you're using bit strings into phenotype space phi. The fitness function, F from phi into the reals, and the genetic operators PC, PM, etc. And especially these, especially the encoding and the fitness function, and how those things are related. Okay, so this is the sort of background thought I want you to have in the back of your mind while we're talking about these things. Okay, so here's some examples from the literature. Well, not all of them are from the literature. One of them is a research problem I'm going to pose to you guys, and if you can solve it for me, that would be awesome, because I've only solved a very small part of it. Okay, so consider a gauntlet thrown. Okay, so some examples from the literature illustrating some key issues. Okay, so the first example, it's not really a specific example from literature, but it's kind of a general factoid. And I like to think of it this way, sort of a general kind of a Grimm's fairy tale title or moral for it is the following. Quote unquote, all bits are not created equal. Okay, so what do I mean by that? Suppose, for example, suppose that your what you want to do is you want to maximize some function that's defined on some interval of real numbers. So your phenotype space is equal to some discretization of an interval. So suppose phi is some discretization, and what I'm going to assume, just to keep things definite, I'm going to let it be the interval 0 up to 8. Okay? And say we discretize this up to a resolution of 1/8. So say to resolution 1/8, and we encode the elements of phi as binary decimals. And for example, say I have this binary decimal, 110.001. I always wonder why they call them binary decimals instead of decimals or something like that. I don't know. This encodes, care to hazard a guess what this encodes? 110.001?
6 and 8.
Sorry? 6 and 1/8. Which I will write this way, 6.0125. Whatever. Okay, so we have everything encoded as a, sorry?
0.125.
Oh, I'm sorry. Yeah, 0.125. You're right. I should have stuck with your 1/8. Okay, so that encodes that. All right, so you have how many places? You have 6 bits, so you have 2 to the 6th elements in phi. So the size of phi is equal to 2 to the 6th. Okay, now I'm mutating these bits. When I do a genetic algorithm on this, I mutate the bits with each one independently with the same probability p sub m, right? But clearly, look, this bit, the so-called most significant bit, if I mutate that, I make a huge jump in phi. I make a huge jump in phenotype space, right? Whereas if I mutate this bit, I only make a jump of 1/8 in phenotype space. So clearly, mutating the leftmost bit implies a big jump in phi. And the rightmost bit implies a small jump in phi. So the effect of a mutation on different bits is going to be much different depending on what the bits are. Now, this is not generally the case in biological evolution. It is sometimes, because you could have a piece of a genome that is like a controller gene that pleiotropically influences lots of other traits. And if you mutate that, you might have some kind of macro jump in phenotype space, but more likely what's going to happen is you're going to have a non-viable creature. So that creature won't even make it to the next generation and get worked on by selection math.
Well, why does this matter? Like, are you assuming that like 6.125 and 6.250 are more similar than, for instance, 1?
Yeah. Generally, for reasonable fitness functions, close together things are going to have close together fitnesses. And if you think back to Metropolis and all those things, the initial perturbation, the proposal step, was always in a small neighborhood of what you were at now. Okay, so generally, the kind of exploration you want to do, you don't want to take sort of haphazard random big jumps. You want to maybe take an occasional medium-sized jump, but you don't want to be bouncing all around with some random probability. Okay, so that's generally what's going on here. Let me codify that just a bit. So a reasonable Fs will generally have the following property, that if you have a small jump in phi, then you're going to get a small change in F value. And there's sort of nothing, there's no guarantee either way about if you take a large jump in phi, you'll get a large jump in F value, whatever. But this will be generally true. And most of the random search kind of things work better when you take relatively small jumps, at least at the beginning. Okay, so generally, in random search, which essentially is what these genetic algorithms with exogenous fitness functions are, it's better, especially early, to make sure to take smallish jumps in your search. And the jumps in your search in a genetic algorithm generally arise from mutation. Okay. Now, one thing that they have done, and this is related to Drew's question earlier, people have used different mutation probabilities for the different bits in an encoding when you have bits that are obviously more significant than others. So one approach that people have taken, so this has been used, is employ different P sub m's for different bits depending on their significance. And here I'm using significance in the technical sense. You know, most significant bit is the leftmost bit in this kind of a string. Least significant bit is the rightmost string. Okay. But here's a question. Now I'm going to pose you the research problem, basically. Here's another kind of approach. So here's another idea. Suppose your phenotype space has some natural notion of nearest neighbor, just like that interval over there. So more generally, suppose phi has a well-defined nearest neighbor notion. And the simplest example of this is, say, phi is a graph, just like the one we had on the prelim the other day for that Metropolis-like algorithm. So let me just use that graph. Why not? Let's say it looks like this, where the nodes are the phenotypes. So phi is the set of nodes. And nearest neighbor relation is indicated by there being an edge between the two nodes. So this node, its nearest neighbors are this, whereas this node only has two nearest neighbors, that kind of thing. Now, why did I pick that graph? Well, it turns out graphs like this model the following kind of phenotype space. So this phi, this graph, models what I call a quote-unquote eggs in baskets phenotype space. What do I mean by eggs in baskets? You have m eggs and n baskets. So m eggs and n baskets. You can think of this as sort of a resource allocation problem. Your resources are the m eggs, and the targets you want to allocate the resources toward are the n baskets. Or you can think of it as an investment portfolio, right? All the different baskets are all the different funds you can invest in. The m is how many dollars or how many units of investment you want to put in each fund. Okay, it models many interesting situations. So it's like a resource allocation where m is the resources and n are the uses for them, target uses. And you want to allocate your resources optimally. You want to allocate the m eggs between n baskets optimally. This particular graph represents 2 eggs in 3 baskets. Okay? This is both eggs in this basket. This is both eggs in the second basket. This is both eggs in the third basket. And the intermediate ones are 1 egg in this one, 1 egg in that one, 1 egg in this one, 1 egg in that one. Those are the meanings of those things. So the graph above, we have m equals 2 and n equals 3. Generally, m is going to be a lot bigger than n, but whatever. That's just a simple example. Now, the nearest neighbor relationship between phenotypes here, in terms of eggs and baskets, yeah, Paul. Yeah. This is both eggs in basket A, say. This is both eggs in basket B. This is both eggs in basket C. Right? And then if I move one of the eggs from, say, basket A to basket B, then I get this point. This is 1 egg in basket A, 1 egg in basket B. Okay, so the neighbor relation, so nearest neighbor corresponds to moving one egg. You take one egg and you move it to another basket. Now, you might remember there was a homework problem that was sort of like this. You had some balls in a box or two boxes. You're moving between them, right? Anyway, so I have all these baskets. I have all these eggs distributed. And if I want to test a new thing, I move one egg and see what the fitness of that allotment is, and so on. OK. So here's the research problem. Here's a problem. What I want to do is I want to design an encoding that avoids macro mutations. And what do I mean by that? I want to find the smallest capital L, that's going to be the bit string length, for which there exists an encoding G from the set 0, 1 to the L. So it's going to be encoding in terms of L bit strings into phi with the following property, that if I make a 1-bit mutation, I move at worst to a nearest neighbor. Never more than that. I may stay at the same place, but if I move only as far as a nearest neighbor. So that any 1-bit mutation results at most in a jump to a nearest neighbor. OK. Now the conjecture is, and I've proved this for some small cases, but not for all, that L is equal to m times the upper integer part of the log to the base 2 of n. OK, so Drew, prove that for every given n. OK? And we can write a paper together. OK. Now, let's look at this particular graph as an example. How many guys in phi? Well, there's 6, right? So I could encode all these guys with 3-bit strings, because 3-bit strings, there's 8 of those. But there's no way to encode them with 3-bit strings so that 1-bit mutations don't lead to macro jumps. OK, so for the graph above, you can't do it with 3 bits. It violates that inequality. Can't do it with L equals 3. But here's one that works for L equals 4. And I'll just tell you exactly what the encoding is, and you can probably see what it is after I write it up. You don't have to write this. I just think this is a cool problem. Anyway, I'm going to put, this is going to be the all zeros. And this one is going to be 0, 0, 1, 1, or 0, 0, 0, 1, 0, 1, 0, 0. This is going to be 0, 1, 0, 1. And this is going to be 1, 0, 1, 0. And this one is also going to be 1, 1, 1, 1. And I don't want to write it up. But the point is, you can do it with 4. It takes too long to have to write up 16 bit strings. So you can do it. And if you want, I'll send it to you. OK. So to me, that's an interesting problem, because essentially what we're doing is we're trying to rig up a genetic algorithm encoding so that when it does jump by mutation, it doesn't jump too far in the phenotype space. And that's wired in. OK, so you can see that the encoding is important here. All right, so that's just one example. So here's another example. So this is a completely different story. So another example. And the moral of this one is going to be that depending on the encoding, schemas may tell you the story about how it works, or they may not tell you the story about how it works. So another example, and this is due to this guy, Lee Altenberg, who, when he did this, was at the University of Hawaii. I'm not sure if he's still there, but I want to give him due credit. Okay, and I mentioned this already in class, but let's go through it. Everybody knows that, you know, if you have a shower setting, like just a shower that you want to get in to bathe yourself, right? There are different kinds of ways of having it set up, okay? So how do you, quote unquote, encoding showers, okay? You can have, and this is how most of them are nowadays, you can have something that controls the volume of water coming out, so it's not too hard and not too soft. And you could have something encoding the temperature of the water. And usually those are in the same switch. Like if you pull it out farther, the shower gets harder, right? And then if you turn it to the right or the left, it gets warmer or colder or whatever. Or you could have a hot and a cold switch. And you could turn them up so that you've got the perfect volume and the perfect temperature, right? Got that? So you're encoding showers. So one kind of encoding is what I would call the volume temperature encoding. So volume and temperature. Okay? So suppose that each of these parameters, volume and temperature, has 5 possible values. And let's call them A, B, C, D, E. So each of VT has 5 values, say A, B, C, D, E. Okay? And the one where you have C and C is the best. C and C is the best. So C and C has fitness. Let me make a little table here. So this is the setting, and here's the fitness. CC has fitness 10. That's your ideal shower. Middle volume, middle temperature, right? Now, if you're me, you would probably want high volume, high temperature, you know, but different people are different, you know. Some people want a cold shower, whatever. But CC has fitness 10. And suppose that you get one of the things right, like volume right, but not the other one. Let's assume that has fitness 5. So I'm going to have CA, CB, CD, and CE. Each of those is going to have fitness 5, as is AC, BC, DC, and EC. So you get both right, and you get one right for these. And say all the rest have fitness 1. They're highly unsatisfactory showers. Okay? Now in this case, you can sort of see that the schema thing is working here. The schema C star and the schema star C both have relatively high average fitness. And this issue about the schema having more members than a typical population here is not going to arise because you have so few bit strings. In this case, it's not really bit strings. It's like quit strings, maybe. What would you call a 5-ary arithmetic? Quits? Anyway, okay. So here the average fitness, static average fitness of C star, that schema, and star C, both of those are going to be what? Well, you have to add up the fitness of every string in the schema and divide by the number of strings. So it's going to be 110 plus 4 5s. And this is not coming out right. It's supposed to come out to 14/5. Maybe I gave different numbers last time I did this. Oh, 6. You're right. I didn't. Okay. So it's the next one that comes out 14/5. Static average fitness of these are both equal to 10 plus 4 times 5 divided by 5, which is 6. Okay? And you can show that the static average fitness of any other schema is way less. Like, for example, A star. Okay? The schema A star is going to have exactly one guy that gets fitness bigger than 1. And all the rest are going to have fitness 1. So it's going to be 5 plus 4 divided by 5. Which is 9/5, which is much less than 6. Now let me make sure I did that right. Based on, yeah, okay. So in this case, you kind of do expect, if you run a GA on this, you kind of do expect, if you use fitness proportional selection or whatever, that the schema C star will arise, the schema star C will arise, and then they'll cross over, and voila, all of a sudden you'll have a shower. Your population will feature the CC shower, and that will quickly propagate because its fitness is so much bigger than everybody else. End of story, right? So thus, in this case, you kind of expect the schemas C star and star C to proliferate and then cross over and whatever. So the schema would seem to give you a good idea of what's going on. Okay, now let's look at the other encoding, the more old-fashioned encoding of a shower, the hot-cold encoding. So here's another encoding. The HC encoding, and I'm going to use HK because C is already used. Okay. So that would be hot and cold. Okay. In German it would be kalt. Heiß und kalt. Right, Andrew? Yep. Do you have German speakers in your immediate family? No? No? Okay. Well, I'm sort of psyched that you actually pronounce your name Knaus rather than Naus. Like, our vice provost for something plus the grad school dean's name is Barb, K-N-U-T-H, and she pronounces it Knuth, which to me is really weird because Donald Knuth, those of you watching at home might know this, is a famous computer scientist who wrote, you know, the first book on the theoretical computer science, and is still the Bible. And he pronounces his name. And he also invented TeX, which is the kind of the Paleolithic version of LaTeX, which is what we write all our handouts and stuff in. So anyway. Okay, so Barb Knuth. She's a really nice person, but she pronounces her name. All right, so anyway, the HK encoding. So here you have 5 settings again. So again, each has 5 settings. A, B, C, D, E. And what is the perfect one? CC is again the perfect one. Okay, and our fitness function is the same. It's the same on phenotype space, but because of the different encoding, it's a different function of strings. All right, so how does that work? CC, still, middle temperature, middle volume is going to correspond the same as middle hot, middle cold. That's still going to have fitness 10. Now, the ones where you get the volume right are going to be the following. It's going to be lowest hot, highest cold, right? Second lowest second lowest hot, next lowest cold, and then CC is going to be the middle one, and then you're going to have DB and EA. Those are going to have fitness 5. These get the volume right. And the ones that get the temperature right are going to be equal hot equal cold. So AA, BB, DD, and EE also have fitness 5. They get the temperature right. And the rest are going to have fitness 1. So you can see that even though the fitness function on the problem solution space stays the same, because we have a different encoding, the fitness of different encoding strings is going to be different from the other problem. Okay? Does everyone understand this? Okay, so let's look at the schemas.
One question.
Yeah.
If you get the volume right but get the temperature wrong, is that why you're...
That's what these are. These are volume right, temperature wrong. So volume right, temp wrong. And these are temp right, volume wrong.
Is that why you have fitness 5?
Yeah.
As opposed to...
Yeah, that's same as over there. The volume right is the C in the first position. Temp wrong is a non-C in the second position. Yep. Okay. So if you go through and you figure out the static average fitness of a schema C star, now is where you get 9/5, I think. So the static average fitness of C star and star C are what? Well, both of those are going to have CC in them, and all the rest of the elements of those schemas are going to be in this slag heap of showers that have fitness 1. So it's going to be 10 plus 4 times 1 divided by 5, which is 14/5. And if you compare that to some other schema, like A star, so other schemas, so let's look at another one. For example, A star. What is the static average fitness of A star going to be? Well, you're going to have two strings in A star that get one of them right. AE and AA. And the rest of them are going to be in the slag heap. So you're going to have 2 times 5 plus 3 times 1 divided by 5. So that's 10 plus 3 is 13/5. See, this is almost the same as that. Okay? Hang on, let me just make sure I got that number right. Does anyone have a question? Oh, you just said, bless you, Matt. Okay, I'm sorry. Yeah.
I'm not sure I understand this encoding.
Yes. Okay. Hot and cold. You have a hot switch and a cold switch, and then you just turn on the shower, right? And say that this is the lowest of each of them, and this is the highest of each of them, right?
Okay, so like if you turn both all the way up, you're going to have the greatest volume at like middle temperature.
Well, if you turn both of them all the way up, you'll have, that'll be EE. That gets the temp right, but the volume is too hard.
Right, okay.
Except for me, because I like it to be hard. So it's almost punishing. Okay. Punishingly hard showers. See, but see, there's no reason based on this comparison to expect C star and star C to proliferate. So schemas, so you don't expect C star and star C to proliferate because they don't have real, comparably much higher fitness to other schemas. And in fact, if you try to run a GA with this encoding for the same problem, different encoding, so the GA with the HK encoding, it fails to find CC as well as the GA with the VT encoding. What's that?
I said it must be why showers typically have the VT-like encoding now.
Yeah.
They used to have their...
Because they decided people operated like GAs, and I don't know. So the GA with the VT encoding. Okay, so what we did was we kept the same phenotype space, the same fitness function, but changed the encoding. And we saw a vastly different behavior. One of the behaviors seems to reflect schema theoretic type reasoning, and the other one doesn't. Or the other one kind of does, but the moral of the story is that it's not just about the problem space, it's not just about the fitness function, it's all about the encoding. And that's pretty obvious when you think about it. And so what I want to do is I want to tell you about a sort of an early view, and I think this is kind of a misguided view, way of thinking about genetic algorithms. And this view was propagated by Goldberg, and I'm really dumping a lot of heat on Goldberg. I did last time, and I'm doing it again. Goldberg was Holland's student, his first student who did a lot of work in this area. So think of Goldberg as the father of this way of thinking. And he wrote the first book on genetic algorithms that was widely accessible. It's called Genetic Algorithms in Search, Optimization, and Machine Learning. And it doesn't contain any math errors like Holland's book, but it does contain a lot of, in my opinion, errors of reasoning. And I call this the multipurpose algorithm mindset. So let's call it the MPA mindset. Okay, so what is this? What is this? And I'm giving you, I admit it, it's a rather cartoonish view of this, but I think it's fairly accurate. All right, so you have a fixed phenotype space phi. And you have a fixed encoding of phi in terms of bit strings or whatever. And you have a fixed variety of genetic operators. So e.g. PM, PC, you pick a kind of crossover to use, whether it be 1 point, uniform, 2 point, PM, could be small. You might be able to tune these things, but whatever. And you think of this as in a box. This is a piece of software that some computer scientists like Robert, right, will sell you. Here's a multi-purpose algorithm. And you can use this to solve lots of different optimization problems over phi. So someone is going to sell you this box and say, here's a way to solve all kinds of optimization problems in phi. So use this box, use this multi-purpose algorithm to optimize a variety of fitness functions f from phi into the reals. Now, why might here? Let's think of a physical kind of example of this. Suppose, say, you are Kirkpatrick, Galat, and Becky at IBM. You're designing chips. You're designing microprocessor chips. So your fixed phi is chip layout space, right? Now, clearly, if you're making a chip to do one thing, like control an airbag in a car, you're going to want to have a different kind of a chip than if you're making a chip to, say, I don't know, have a memory on it or something. I don't know anything about microprocessors, so whatever. So the point is that in chip space, suppose, for example, phi is chip space, chip layout space. Different f's would correspond to different sort of chip specs, which are going to be different depending on what you want the chip to do. So they depend on the chip's, whatever you want to call it, mission, so to speak. You're going to have a different fitness function. Different layouts are going to be more fit for one function and less fit for another function. And Goldberg has sold you this box, and it's an algorithm, it's a piece of software, whatever, and all you have to do is type in the fitness function. And then it's going to Trevor.
So
process here like actually completely optimal, or just
performing as well, you know, like certainly there's going to be, you're never going to be able to perfect something, right? But, and sometimes, actually, I wish Cameron were here because he told me the story about somehow they used a genetic algorithm to design an FPGA that was logically the same. All the connections were exactly the same as another FPGA that had a different sort of physical way of putting the things, but they performed differently, and the one that the GA design performed better because of some weird fields that were around. You know, have you heard of this? Vaguely?
Yeah. He told me the same story.
Yeah, I'll wait till if he comes back. He'll come back after spring break probably, so he can tell us that story. But I thought that was kind of cool, actually. You know, it's all right. So, but anyway, the point is, that's that view. Now, what's wrong with that view? We just saw what's wrong with that view. We just saw. We have shower space, right? But we saw that for different encodings, the same exact F, the problem would not be solved by this multipurpose algorithm because of the interplay between F and the encoding. So the shower example shows that this is kind of a flawed view. It's really about the encoding and the fitness function, that you have to redesign the encoding for different fitness functions sometimes so that you get a GA that works. So the shower example, and that's a really simple example, shows that the encoding is just as crucial as the fitness function. They work together. Okay, so carrying on with this kind of misguided view, Goldberg defined a problem to be GA hard. So Goldberg defined a problem, and here in this case, that is to say, choice of fitness function, as GA hard. And actually, Mitchell uses this terminology later on in her book. And this is kind of old-fashioned terminology, but this is an example of the kind of wishful thinking people were doing. He defined it to be GA hard if, when you took the multipurpose algorithm with its fixed phi and a fixed encoding phi and you put the F into it, you didn't get good results. So if this MPA didn't do a good job. Maximizing F. And he tried to shoehorn this into a schema-centric view of the world as follows. So he tried to explain it schema-centrically as follows. Okay. Given a multipurpose algorithm with a fixed phi and a fixed encoding of phi and fixed choice of genetic operators. So given an MPA, given the MPA as above, define a fitness function f from phi to reals as maximally deceptive. Okay, and this, again, Mitchell has this in her book as well. If and only if the following statements about it are true. The all zero string maximizes F. But every quote-unquote lower order schema competition, and those are the things that Holland thinks of as running in parallel with each other, this implicit parallelism idea, is one by schemas, all of whose defined bits, all of whose fixed bits are 1s. Okay, and he goes on to prove some results about how if you have this multipurpose algorithm and you have such a fitness function, then the algorithm's not going to work well at optimizing it. Okay? So what is his view here? His view is that there's... Finish this up. Okay, so Goldberg's view here, Goldberg's view I have this great multi-purpose algorithm that I've designed and wired into this box and sold you the software for, and you have a lousy f. So there's something wrong with the fitness function f, this maximally deceptive fitness function. It's not, my algorithm doesn't work on it. It's a messed up fitness function. It gives rise to a rugged fitness landscape. There's all this talk. And that's another thing in Mitchell's book. That's a classic GA piece of GA lore. Rugged fitness landscape, etc. Okay, so that's Goldberg's view. And he probably doesn't hold this anymore, by the way, but he did when he wrote it. My view, on the other hand, our view, with the benefit of 20/20 hindsight, there's nothing wrong with f. Okay? There's nothing wrong with f. The interplay between the encoding and f is what determines whether the GA works on f. So the interplay between the f and the encoding determines how well the GA optimizes f. So in a sense, you know, it's not useful to sell these multipurpose algorithms with fixed encoding G, because depending on what f you're trying to maximize, you might want a very different G. Okay? So depending on what f you want to maximize, you might want a very different G. Okay? So the MPA view of the world is, in some sense, misguided. Okay. Now, we're going to come back to this a little later on when we talk about something called the no free lunch theorem from optimization. Anybody heard of that? It's kind of a famous, yeah. We won't go deeply into it, but anyway, we're going to see what this has to do with that, because I'm actually not quite exactly sure what it has to do with that, but I know it's related. All right, so one more example, one more author. So a final example. These are two examples. These are due to this guy, Greifenstädter. Okay. I don't know what that means. Do you know what that means?
Surprised not an A umlaut.
A umlaut?
Yeah.
Yeah. Let's see. What would Graph be? Yeah, but what would it mean? Anyway, okay. So final examples due to Greifenstädter. One of them is the needle in the haystack example. Okay. And what this is doing is sort of putting the lie to the maximally deceptive notion as being the root of GA difficulty. So here's a needle in a haystack. And this is definitely cooked up, believe me. Okay, so you're encoding with L-bit strings. And your phi is some discretization of the interval 0 to 1. And your f, your fitness function, looks like this. And I'm going to draw phi as if it were a continuum. But what happens is at 0, it's going to be 2 to the L. So I'm going to make this is like a break in the graph. It has value 2 to the L at 0, and then it has value whatever squared between 0 and 1. So this is 1, and this is like t squared. Okay, so the point is the optimum is a needle in a haystack. The optimum is 0. So you max f. 0 maximizes f. Okay? But it's hard to find, no matter what encoding you use on phi. So this turns out to be very hard for any GA to find that 0, no matter how you encode your phenotype space. So it turns out to be hard for a GA to find 0, no matter how you encode phi. However, notice that no matter how you encode phi, for any binary encoding, okay, any schema that contains the string encoding the optimum, so every schema containing the optimum string, the one that encodes 0, and actually let me just say an optimum string, because remember we allow encodings to be many to one. Has static average fitness what? Well, the fitness of the string, it's going to have at least one thing of fitness 2 to the L, and then it's going to have a bunch of things that are non-negative, and then divided by the number of strings in the schema, something less than or equal to 2 to the L minus 1. Because if I have at least one defined bit in the schema, then I have at most 2 to the L minus 1 strings in the schema, and that's bigger than or equal to 2. So any schema containing an optimum string has fitness bigger than or equal to 2, static average fitness, whereas any schema that doesn't contain the optimum string it's 2 because I put a line through my z's for that reason. Okay. Any schema not containing an optimum string has static average fitness. What? Well, it's going to have a bunch of things that are less than or equal to 1. Divided by the number of things and that's going to be less than or equal to 1. Okay, so this fitness function, in Goldberg's terms, no matter what the encoding, this fitness function does not deceive it. Okay, because the schemas that have the optimum are good versus others. So thus, schema theory would lead us to expect that we would find the 0 because we have a good kind of comparison between these static average fitnesses, but it doesn't happen because it's hard for a GA to do that. So this fitness function isn't at all, and I know I'm keeping you a minute late, but it's before spring break, so I'm hoping you're all in a good mood. Goldberg, and if Alex has to leave before I'm done, I'm only going to take like 30 seconds. Okay, yeah. This fitness function isn't at all Goldberg deceptive, no matter what encoding. But the problem is still GA hard. Okay. So that's one example, and then the final example from Grafenstedt, I may skip it, but I may not, is called collateral convergence, and we'll get to that in a week or so. Okay, so I hope everyone has a nice break, including those of you out there, and again, the academic calendar, up or down? I agree. I agree.